Okay, so I'm sorry again that I'm not going to be in class. I will be out for a neurologist appointment starting at 11:10. So this is going to be the lecture for today. And if you don't have your book or access to your book, we're going to do a couple of skill building exercises. So you'll need a piece of paper and you'll need to write the date on top, and it'll be collected at the end. Okay. So we're going to finish up chapter 1. So remember, I told you no talking. So I told you that in the second version of the book, this is chapter 1. In the first version of the book, this is chapter 2. Okay? So I don't know which version you have. Stop making noise. No noise, because this is recording me, okay? My voice. So if you're making noise, it's going to record you too. Okay? Thank you. So we're going to pick up in chapter 1.4, and we're going to start talking about the inside of the atoms. So you remember last time we talked about the fact that there are electrons, protons, and neutrons. So if you haven't watched the other YouTube videos, you need to watch them so we can be all caught up, and then remember to ask questions if you have any. So what we do know about atoms is that they are electrically neutral. And in order for that to be true, it means that there must be equal amounts of electrons and protons, because they are the only subatomic particles that have a charge. So if we have an equal number of electrons and protons, what that means is that our atoms are neutral. And there are some cases where we have atoms that are not neutral, and we'll talk about those. Okay. Now, even though these must be equal, that does not mean that neutrons must be equal. Okay, so it's not that they are all equal to each other, it just means electrons and protons must be equal in order for the atom to be neutral. Now the atomic number is the number of protons. So the atomic number is equal to the number of protons. Okay, so we can look up on the periodic table and we can see that this is the number which should be in red. Okay, so the number on top. So for example, carbon is element number 6, means it has 6 protons. It would also have to have 6 electrons in order to be neutral, right? Because we just talked about this. So isotopes are going to be atoms that are the same element, but they have a different number of neutrons. So going back to our example of carbon, carbon has a mass of 12. Okay, so its atomic mass is 12, which means that some of the weight of this atom must be due to the neutrons. And if you think back to the previous table, we said that protons, we could say, have a relative weight of 1, and neutrons have a relative weight also of 1. Okay, so our atomic mass is going to be a sum of the number of protons plus the number of neutrons. So if we treat it like a formula, 12, which we said was here, and 6 protons, means that our number of neutrons is also equal to 6, okay? And that's for this carbon. But there are different isotopes of carbon. Like this one is carbon 12, so the atomic mass is here, the atomic number is there. But there's also carbon 13, which is used for radioactive dating, like old paper scrolls and things like that. And there's also a small amount of carbon 14. So they have the same number of protons all the way across. They have the same number of electrons all the way across. The only difference is carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. Okay? So there is going to be an important series of isotopes that's found within hydrogen. It's very similar to what we just talked about with carbon. And there are 3. So the first one is hydrogen as we know it. Then there's one that's called deuterium. And then there's one called tritium. Okay? And if we follow the same pattern we did with the carbon, we know that this hydrogen has 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, and 1 electron. Okay? And then we know that because the mass is 1, in order for this formula, 1 equals 1 plus number of neutrons to be true, it means that this hydrogen has 0 neutrons. Deuterium must have 1, and tritium must have 2. Okay. Now, isotopes are most often seen, at least in the medical field, in imaging. Okay. So the other day I had a CT scan of my lungs and heart done, and they used an isotope of iodine that is radioactive. And when I had my MRI, they used a radioactive isotope called gadolinium. So most often you guys will have known it if you've ever had any sort of medical imaging that's done with contrast. So bismuth is another example. And really isotopes are just the same type of element, but they have a different number of neutrons, which makes them distinct. Okay, it's enough of a difference to make it its own kind of distinct element. Okay. All right, so mass number, we've already talked about it, but earlier I called it the atomic mass. So sometimes you're going to see atomic mass, sometimes you're going to see it called the mass number, but it is going to be the sum of protons plus neutrons, okay? And this will give us our atomic mass. And if we think back to our isotopic notation, that was this right here that I showed you. It's always going to be the atomic mass over the atomic number and then the atomic symbol. Okay, so we kind of use a block-like arrangement, okay? So if you think about the element here in the center, the symbol, then we're going to take the information off the periodic table and put it there. Now, if you look on the periodic table, what you're going to see is that the atomic mass, so for example, this is carbon. This is what you'll see on the periodic table if you look up, right? Here's the box. So you're going to see that they flip. So the atomic number goes down there, and the atomic mass goes up there. But here, it's not a whole number because it's an average of all of the isotopes found in nature. But when we write it in isotopic notation, because we're talking about carbon-12 only, we're going to use a whole number. Okay, so that's the difference you see there. So what you want to be able to do is to take any of the elements that we see here, and I want you to be able to determine the number of neutrons, protons, and electrons. Okay, so we're going to do our first skill building exercise here, and we're going to fit it in right here. So get your piece of paper out. Stop. And the skill building exercise is on page 20 of version 2 and page 56 of version 1, okay? But I'm going to write it out here since we're not together today. So what we want is we're given the elements sodium and oxygen, and I'm writing the symbol and the element name because remember, I'm not expecting you guys to memorize all of the atomic symbols and mass. And what it's asking us to do is to identify the number of protons only in each element. And so the easiest way to do this is to look at the periodic table, identify the element, and look at the number, this one, the number on top, and that will tell us the number of protons. So I'm going to give y'all just a few minutes to try that, and then we will go through the answers together. Okay, so hopefully you've had time. If not, we'll go through them together. Maybe you've completed one or two. So sodium is element number 11. It's in the first row. and therefore it has 11 protons. Sodium's in the first column, not the first row. Oxygen is on the far right side of the periodic table, almost near the upper right corner, and it's element number 8. Therefore, it has 8 protons. And chlorine is right catty corner from oxygen, and it's element number 17, so it means it has 17 protons. Okay, so hopefully that makes sense, and you're starting to understand how we can use the protons. Now, the next skill building exercise is on the same page, and instead of identifying the number of protons, this question is going to ask us to identify the number of electrons, and we're going to assume right now that these are neutral. Okay, so if we think back to a rule where iodine is I. If we think back to our rule before, where we said that protons must be equal to electrons if the atoms are neutral, it means that we can use our same trick of looking at the atomic number, and that's also equal to the number of electrons. So I'm going to give you just a little bit of time to identify these and hopefully fill them out, and then we'll go through them together. All right, so magnesium is right next to sodium, which was element number 11, but magnesium is 12, so it means it has 12 electrons. Potassium is right beneath sodium in that first column, and it has 19 electrons. And then iodine is over there on the right-hand side, but it's in the second to last column, and you have to kind of look further down, but it has 53 electrons. Okay, so I'm hoping that this will help you identify protons and neutrons. Okay, the next skill building that we're going to do is about using isotopic notation and determining protons and neutrons from the isotopic notation. Okay, so we have 2. Stop. All right, so our first one is going to be, our first one is going to be gold. And this is on page 22 in version 2 and page 58 in version 1. And then our second one is going to be sodium. And we want to know number of protons and neutrons. So if I look at this first one, I'll do the first one with you and then give you just a little bit to do sodium. So we know that protons must be equal to the atomic number, which I've written here, and that's 79. Now neutrons plus protons must equal the atomic mass. Okay, so I'm going to take the difference between 197 and 79, and that means that I have, that's not right. This should be a neutral. That means that I have 118 neutrons. Okay, now take just a few seconds to do the same thing with sodium, and then we'll see if we get the same answer. Okay, so hopefully we can see that the protons is equal to 11. We kind of did that one earlier up here, but it never hurts to practice it again. And if we use our same formula here, we see that there are actually 12 neutrons, okay? So even though we don't tend to think of this up here, can you see where I'm highlighting, as a formula to know, but it is a formula. It's essentially a definition, but you need to know how to calculate protons, neutrons, and electrons from either the information given here or from the isotopic. So this is called isotopic notation. Okay? All right. So, yes? I love you too. Thank you. So earlier, we were talking about atomic mass, and it's crazy to think about something so tiny as having mass, but it does, even though they are very tiny. So we tend to use what's called the atomic mass unit. So that's abbreviated AMU. Remember, we talked about all measurements. What?
You can like an egg.
Okay.
Like egg? Or like your baby can do that?
Okay, thank you.
Okay.
So earlier we talked about there being, for every measurement, for every number, there must be a unit for it to be a measurement. And so the units for mass is going to be atomic mass unit, which is AMU. So earlier, whenever we said that carbon-12, if I remember up here I drew 6. Okay, remember up there? These were technically the units on there. Okay, so there are units that go with it, but they're called atomic mass units. And the official definition is that one atomic mass unit is 1/12 the mass of a carbon-12. So it is a standardized measurement because we have something to reference it to. Okay, so you'll have units to put with it. And then once we get to chapter 3, I think 3, 4, or 5, we're going to give it a different type of units. Okay, that will help us with mole calculations. So earlier I explained that the reason why it's not an exact number is because we average all of the elements naturally occurring isotopes by taking their percent abundance and multiplying it by the mass. But do not worry about calculating. Okay, I'm not going to ask you to calculate this. But I simply want you to understand why up here we talked about everything being whole numbers, but then when you look at the periodic table, as in here, they're not whole numbers. Okay, and that's simply because of the isotopes, but it should not impact how you do the calculations we did earlier in our skill building exercises. Okay, those are bad arrows, but that's what they should be. All right, so now we're going to talk about the arrangements of the electrons. Remember, we said that electrons exist in the outer area around the nucleus, and so we have something that's very complicated. We're not going to get into it, but it's called quantum mechanics, and it describes the electrons as they exist in that outer area, okay? And so the following statements must be true. The electrons can only have specific energies, and we said that this is a quantized amount, meaning that it's a fixed value. So each electron is going to have a specific value associated with it. And this means that there's a certain amount of energy associated with it moving around. If you think about like fluorescence and phosphorescence, these are things happening with the electrons. And those are moving electrons, and that's why we see light in the form of maybe bioluminescence, like fireflies or glow sticks and things like that. The second rule, Anderson, stop. I love you. What? You have to wait. Come in here and raise your hand first, and then I'll pause it, okay? Yes? Okay. So the second rule is that all electrons are going to be organized into sets called shells. And then they are going to be Shells are a grouping of electrons within the atom. Yes.
Can like add?
Yes,
They're
Anderson.
small?
I know, they are small, aren't they? I heard you earlier, though, okay?
You can say it.
Okay.
Because you can cook stuff.
Can you hand me my drink up there, please?
Yes, I can.
Thank you.
The water.
No, it's not water, but you can't drink it, okay? Because I'm not feeling well, and I don't want you to get sick. Can I please have it?
What is it?
It's Pedialyte. Okay, it's gonna make me feel a little bit better.
Like pee.
Mm-hmm.
Oh my God, you want me quiet it?
Mm-hmm.
Yeah, okay, good.
All right. Okay, I'm almost done. Okay, just a little bit longer. Thank you.
I'm gonna go in my room.
Okay. So what this means is that the electrons don't just exist like willy-nilly around just anywhere, right? They're going to have specific shells or homes. And so for better or worse, we're going to go back to this planetary model, right? Remember we said this isn't exactly true. What it means is the electrons are going to live in shells, okay? So something like this, and this is not perfect, but as we go from elements like hydrogen to lithium, we're going to add electrons, but then eventually we're going to fill a shell, and then just like you would fill a dorm, and then we have to fill the next shell. Okay, so once we fill the inner one, if we go to say boron, we have to make a new shell, and then we fill it all the way up till say we get to sodium, and then we have to fill a new shell, okay? And it gets bigger and bigger and bigger as the elements get heavier and heavier, okay? So that's the second rule. And the third is that these shells are divided into a subset called subshells, and this is a grouping of electrons within a shell. So if we think back to this, like this first shell right here, it's going to have a set of subshells, just like this will have a set of subshells, and just like the third one will, okay? So it's kind of like if you lived on a street and you had a house, right? A certain number of people are going to live in the house. Maybe there's 2 stories, and then within each room, you're going to have people that are there, or maybe your dorm, okay? So in Centennial, there's 4 floors, and I don't even know how many rooms are in there, but then within each room there are people living in each room, okay? And electrons are kind of similar to that dorm analogy. And then the fourth rule is that different subshells hold a different number of electrons. So we have the S subshell, which is a nice spherical subshell, and then we have the P orbital, which is shaped like a dumbbell or a bow tie, and then we have the D's. And these are different shapes, but most of them are kind of like a 4-leaf clover. Mine's not very pretty. See if I can do a better job. It's a little bit better. And the F's, which I'm not even going to try to draw that well. They're very chaotic. But these are the subshells. Okay, so they have different shapes and they have different names. The S, the P, the D, and the F. And we'll see a little bit more on that later. Okay. So now we're going to have a skill building exercise where we are going to talk about electron configurations. Okay? So electron configurations are a shorthand description of the arrangements of the electrons in an atom. Now, most everything that we're going to describe this image right here. Okay, it's like giving an electron a mailing address. Now, most of all chemistry is really associated with just the outermost shell of electrons, so that would be this outer ring right here, because they're the only ones that can really be exchanged in the event of a reaction. And so we call this the valence shell electron. Valence meaning outer, and everything that's not in the valence shell. So let's see if I can pick a different color. So this is the valence shell. And everything that's not in the valence shell is considered to be a core electron. Okay, so they exist at the core, and they are not usually participating in chemical reactions because they're held very tightly by the nuclear forces right here, and so they're not going to be usually exchanged or shared in chemical reactions. Okay, now electron configurations are kind of confusing, so we're going to go through the periodic table, and I'm going to use this one right here, and then you're going to have one as well, and you're going to feel free to label it as best you can, and